And one more little bit of preparatory work and we will get started. So those of you that just joined us, good morning everybody. Go ahead and say good morning in your favorite language in the chat box. It will be graded. No, it won't. Content folder. Lesson 12, section 03. Oh, one more quick edit, give it the proper name. Oh, Dooley said good morning in Rambosian. I'll let you all ponder what book that came from. One extra credit point today for somebody who can get the name of the book or the author of The Language of Rambosian. R-A-M-B-O-S-I-A-N. Good, that'll keep Google busy for a while. Okay, that's built. And then finally the link. And copy that. Web link. Okay, and let's see, back to the Zoomster. Turn on my screen and we will begin. So video's running, share screen. Try something dangerous today. Okay, lesson 12. Okay, so I'm at the Blackboard site. Welcome everybody. Anybody found out about the language Rambosian? Okay, we'll save that maybe for later in the lesson. It's not, oh, Ben Rush, extra point for you. Egg book, not bad. So he got the author Jasper Ford. Did you happen to know that, or was that the result of a Google search, Ben? It might have been Google. Okay, interesting. Okay, so we'll get started with the lesson. I have the recorder running. Good morning, everybody. Welcome to lesson 12 of ENGR 1330, fall 2020. And I hope you all had a great weekend. It was real pleasant weather this weekend. And we're getting on into fall, so we'll have more of those pleasant days, and then it's going to get cold. Well, comparatively cold. Cold we're not ready for yet, and then we'll be complaining about it for a few weeks until we adapt. Today's lesson is on a topic called descriptive statistics, and it might seem a little easier than you're used to, but that's okay. We have plenty of not so easy stuff coming up soon, and this seemed like a really good. It's not insert in here as a break. It's a logical sequence, so we'll go through the lesson shortly, and then you have a laboratory that will follow immediately after. And if I don't take the entire hour and 20 minutes, we'll do the usual and we'll segue straight to lab after a 10-minute break. Because the question is going to come up on your exams, they're graded, and I am still looking through every one of them in a supervisory role, and when that's complete, I will go ahead and activate the grades. So don't go typing when the exam's going to be done. They're done. For the most part, the class collectively did quite well, and as when the grades are posted, most of you, I hope, will be satisfied. There might be a few that will be unsatisfied. Your usual solution to that is to learn from the performance and adapt for the next exam. There's plenty of graded material in this class. There's no reason to do poorly unless you don't come to these calls. Don't watch the videos in their entirety if you choose not to come to the call, and don't do the exercises. In that case, we have no sympathy for you. So let us begin. So I have to do one more activity. I apologize. I need to share this with the other instructors. So I go here, I copy it, share it with the other classes, and yeah, it looks like I have set it up. And if I do that, it goes to the right place. Choose the okie dokie. There we go. So, descriptive statistics. And if we go to the, I need to actually open up the link to the lab. So you're going to watch me do one more thing. Okay. Someday it'd be really cool to actually teach a class in the PHP programming that's going on that makes these web pages. So I just need the content thing. And that was wrong. Try this again, content folder. Yay. Go into the content folder and produce a web link. Web link is to lab. Yeah, that's kind of a good thing I did that, because that web link goes to nowhere. I'll fix that in a second. All right, now everything is where it's supposed to be, and man, I actually feel for y'all having to do everything in Blackboard in your other classes. This thing is just awful. So there we go to the lesson, and that looks correct. PowerPoint's empty because I haven't uploaded it yet. And Lab 12 is coming up. Oh, my bad. Works better if it has the correct name. Funny how that is, huh? Yay! All right, we are good to go. And that was only 10 minutes of programming while you watch. and this is supposed to be lesson 12. Well, that's supposed to be lesson 12 also. I will fix that next time I actually get to the repository. So here's our lesson 12, and I'm going to do something a little different today. Not fundamentally different. I'm going to download the notebook to my computer and then share my entire desktop, and I'm going to run it on my local copy of Anaconda. So I want to save link as, and let's put it onto my desktop. This is one thing I detest about it. I want to go to desktop. There we go. Save that, and I'll have to save. So usually when you find a data file, it's probably part of the lesson. So I'm going to go ahead and download and save that. Save the file. And the only problem is I'm going to have to find it because it's not going to save it to the desktop because it's a computer and its purpose in life is to make me want to provide carbon sources for its energy. So now we've downloaded to my local machine. So I'm going to minimize the browser window. So in the past, Farang and I have both been using CoCalc. I've been using my personal Jupyter Lab hub that is located on Amazon Web Services server. But today, just to be different and to reinforce that you can do it on your local computer if you've installed your Anaconda deal, we'll do it locally. And then if it fails, obviously I'll switch back to the I'll switch back to the cloud-based thing. So here's my highest grossing movies, and I'm looking for, that was not bright, Dr. Cleveland, because you're going to have a heck of a time finding the actual file. There it is. So there's the file. Let me make a new folder for it. And I think on Thursday we'll do the same thing, except I'll do it in Windows. So I will be adapting to all of the computational system. My desktop is actually starting to get cluttered. And that you'll experience that too. The easiest way to manage clutter is to drop everything in a folder and put it onto an external drive. So there's my setup. So on my computer, I'm going to have to go to Applications and launch my Anaconda. And then in the chat box, Farang is giving you the necessary files and labs that you'll need for the lesson and for the lab. So we will launch this Jupyter Notebook. On the workshop video, how this is all arranged is explained briefly in there. There's also a supplementary video that was uploaded late last night that shows how to convert HTML to PDF files. That was actually a good finding because now you don't have to get a working LaTeX running. So what I did when I launched my Jupyter Hub, currently, if I look at the URL, it says localhost 8890. Actually, I kind of don't understand why it selected that particular port, but so be it. So localhost means that there's a web server running on my laptop. So the laptop is pretending it's Google for all practical purposes. And the Jupyter environment is supported on port 8890, and it's going immediately to what it calls tree. It's like the web root. And if I look here, we have a file system that admittedly is a little more complicated. Not complicated, it's different, so it takes a little while to figure out what's going on. But I want to go to my desktop because that's where I loaded the file. And here I left a directory called my lesson12. And so now I have the files there. There's lesson 12. There's highest grossing movies. So if I select lesson 12 and launch it, oh, I didn't think this. Oh, good. I initially didn't think this out. I wasn't sure if the graphics were going to come through, but I guess my computer does have access to the internet. And so here is our lesson for today: descriptive statistics, and we're using Python as the computational tool. Made this nice, cool picture that largely this lesson was created by your lab TA Farang, and I'm kind of just the mouthpiece, so I'm sort of reading it. I've seen it before, so I won't be completely blindsided. And just by way of mention, so this stuff up here, we haven't taught you how to do that, and actually I'm not going to, but you'll find on many of our worksheets we have a block at the top that's labeled exactly this, as script block to left-align markdown tables. That's to make any markdown cells that you create have the correct aesthetics. So other than that, that's all that piece of script does. And the other one, you notice I always usually have a preamble. Its purpose in life is to be sure that is to allow us, if we're helping you debug the script, to know what machine you ran it on and what kernel version it was using. Oh, that was a big yawn for somebody. I sympathize.
Dr. Cleveland, I think the main server is down.
The 54243 one?
Yes.
Let's find out if that's good observation. Let it reboot, everybody. Don't try to make a request from it now, because it'll just get all buggered up.
Bless you.
Yeah, there's going to be a lot more sneezing as the season changes. It's definitely not responding to inputs right now.
Yeah, I think we kind of simulated a cyber attack on your server.
Yeah. But as far as I know, it's not programmed to stop anything. Okay, that's my local Jupyter notebook. That's my remote. Let me see if I can actually get any control at all. That was a disconnect, so that doesn't require it to do anything. Yep, it's clobbered right now. Well, we'll have the fun thing of trying to remote manage a server. Yeah, it's definitely quite clobbered. So I need to get to the controller. So what's going to happen for everybody listening in, I'm actually going to stop the server and restart it. So if you have pending connections, you're going to lose them. The best thing you can do right now would be to close your individual tabs on the browsers that are connecting to the 53, let me get to actually with the URL, that are connecting to 54.243, 259.9. If you don't want to, that's fine. I'm going to force a disconnect anyway, but it will work better. And I'm not going to make any complaints about CoCalc. I never built this and attempted to build it to support 100 concurrent connections, so I am not worried about it. Password. What is my password? Vladimir, what's the password? I think that's it. I don't want to have to look it up. Okay, so the management software is still running. That's a good thing. Says my server's running. Let's do a quick look to see if I can tell what's going on. So 8:20, that was 4 minutes ago. I had plenty of clock cycles remaining. See if I can connect from here. And looks like that's going to be a no. So what I just did doesn't always work. Trying to regain enough control. There is a trick when you're managing cloud accounts. If everything just becomes uncontrollable, if you stop it for a few minutes, you can regain control. But the problem with stopping, as you saw, I had 160 minutes of unused CPU cycles. I lose all that if I do a stop. So what I usually try is a couple of reboots. And then I'll probably will end up stopping and restarting. Oh well, we don't have time to wait, so it takes a few minutes for the stop to complete, and it's going to take a few more minutes for me to restart. So during those few minutes, I will slowly work through the descriptive statistics lesson, but only very slowly. So just listen. So a fundamental part of working with all the data that we're going to and that you're going to in your careers is being able to describe it. So descriptive statistics are a way to summarize large quantity of data in a sensible manner, and you've seen that on TV when they describe the results of double-blind studies for COVID-19, vaccines. They can't go through every individual study and do the 12,000 people, and each of them had 3 hands and 2 legs. They summarize that, so they have the performance for all the 3-handed, 2-legged people that were undamaged by the vaccine and so on. So that is a use of descriptive statistics. And here's a few meaningful documents that you can look at. One is called Descriptive Statistics with Python and Numpy by Rashmi Jain, and here is a link. And what's cool about all these links is they don't go anywhere. I guess you can guess where the picture came by. These are actually blogs. You would be amazed at how much you can learn from other people's blog placements. So the person goes through a few examples and shows you how to do it in Python, as much to including full Python script. Now this is pretty cool. Y'all may not notice it, but with this 3-arrow input, this was actually done. He cut and pasted out of an idle integrated development environment editor, because it has a pretty unique cursor model. And then he does it for a few others. And so the point is, there's a lot of blog information that will largely do what you need. And you just have to be not only creative in your search terms, but be a little persistent to quickly go to a link and decide if it's garbage or not. And you can usually tell pretty quickly. So here's a second one in Python, how to describe data. And I'm curious enough of that, we'll take a look at it. Actually, mostly what I'm looking at is the cool graphics that each blog person uses. This one's nice because it's all has a table of contents, and as you work your way through, there are going to be examples and a set of examples. So normally, I think what you will find when you're searching is a blog is going to be useful to you if there's actual examples. If it starts to look like an owner's manual for a mainframe computer, which is what python.org will look like, it's not going to be useful. You can skip it and go look for something else. Next one is Quick Guide using Pandas and Seaborn. Seaborn is another package. Actually, we used it a while back for making a really cool plot. And same thing, there's probably examples. My network is struggling to load stuff in a reasonable amount of time. Data, and then in his case, he's chosen this particular markdown environment to show the Python script. And the last one is a tutorial basic statistics in Python. And again, examples. So when I was in college, like you guys are now, this idea of examples, that hadn't emerged yet. And it was like there was one example in the book, and somehow you're supposed to figure out how to do stuff. So I'm jealous of you in that you have this immense resource of already worked examples that pretty much, if it's not a direct answer to the question that you're actually asking, it's close enough that you'll be able to adapt it to your specific needs. So I've stalled good enough. Let me see if I can regain control of my server. And the miracle of cloud computing is happening before our very eyes, but we don't see it. There's little teeny squirrels out there. I think this is in the Virginia server farm. They're stretching and now they're cranking on little wheels, and they're throwing nuts into a hopper, and they're striking a match, and it's burning a flame, and now we have our computer running again. Yay, okay. Okay, that should do it.
Yes, it seems to be working.
Okay. So I will exit that and go back to my lesson 12.
And Dr. Cleveland, you're recording this, right?
Yes, I am.
Thank you.
So we're going to look at a data set called highest grossing movies as an illustrative example. And let me see if I can open the file in its most native form. So here it is. It's not a very long file. So it has a header line, which is movie, director, year, budget in millions of dollars, and then the gross in millions of dollars. And then it has Gone with the Wind, Avatar, Titanic, and the various directors, the year of distribution, and the money thing. So that's what a comma save value file looks like rendered as a text file, which by definition they really are. Now how do I get out of that? There we go. Click on that doodle. There we go. So we're going to go ahead and read that file and then explore some various measurements of that very small database. So the database was selected to be small enough that we can see it, but big enough in the sense that it would be a real pain in the neck to calculate certain things by hand. Not impossible, just a pain. So we'll import the necessary packages. and I clicked it, and you notice that thing briefly went into asterisk form, and then it got done. And bear in mind, I'm running on my local laptop now in Anaconda, and when we get to the end, there's a reason I'm doing that I'll share with y'all. And now we're going to use the read, save value method in Pandas. So PD read, save value, and then we have to provide the file name. There's other input parameters we can provide, but this will do our job, and we're going to assign it to an object named. This is the interactive mode. What's the object going to be named? It's mostly to see if the 70 of you are even still paying attention. Very good, Max. Excellent, Braden. Actually, Max is the only one that got it correct. It's capital M movies, which is it's just an object. I believe the convention is we're trying to avoid capital letters, but I don't really care. There's a Python, real whiz-bang Python programmers get all torqued when you do that. Fortunately, we're all self-taught, so we don't really care. So we've gone ahead and we've assigned it to the object, and we just printed the object using the Jupyter Notebook, where if we just type the object name, it will print it the best way it can. And we see that there are 10 rows in it, or in the database world, those are called records. So there's 10 records, 1, 2, 3, 4, 5 fields. Each column in a database is called a field. And then we have the movie fields, the director fields, and so forth, all populated. So we're now going to summarize that database using a couple of different metrics or measures of it. Three of the important features of data that we want, especially if it's numerical data, is we want to know some measure of its central tendency. Central tendency being if we were to blindfold ourselves and start reaching into the data and just grabbing things and pulling it out, what's the average value of the thing we'd pull out? That's what a measure of central tendency is. And then if we have a data model of the data, an example of a data model might be the normal distribution. Central tendency tells us where that normal distribution model is located on the number line. The second thing we want to know about data is what's its variability. So if using body temperature of a human being as an example, I believe the central tendency for that is somewhere around 37 degrees Celsius or 98 degrees Fahrenheit. But the variation matters too. Everybody you measure is not going to be at 37 degrees Celsius. And what we're concerned with variation, if you were to measure a body temperature of 10 degrees Celsius, I think you'd be a little concerned because if that body's moving, you'd be wondering why it's even alive, because that's kind of low. Likewise, if you measured one at 70 degrees Celsius, that's in the 180s or something in Fahrenheit, you'd be wondering why the body has not spontaneously burst into flame. So it's the whole zombie thing. So the variation is an important measure of the database, and some of the metrics are listed here. And then the last one we'll discuss is the shape of the database, or the shape of the data model. Try to keep in the back of your mind that all these data, we're trying to build a model of the data because the model gives us some additional capabilities that the data itself doesn't. We're worried about the shape, whether it's a kind of a pointed bell curve looking distribution like you've probably had in your other classes, or if it's got two peaks in it, we call bimodal, or if it has a bunch of peaks in it, or if it's all squished to one side or the other of a number line. So central tendency, variation, and I call this asymmetry, but shape seems to be the more correct terminology. in the measures of central tendency, we have arithmetic mean, which you're all familiar with. That's what you all call the average. That's what I call an average. And I think in common discussion, if you ask someone for an average of something, they mean the arithmetic mean. But there's a couple other measures of central tendency. One's called the median, and the median is a value that divides the collection of data into two parts, a part that's smaller than or equal to the median and a part that's bigger than the median. So the median represents the 50th percentile quantile of the data. Mode is the measure of where the pointiest part of the data is, the most frequent observation. We'll look at some pictures of that. And then there's a few other types of means. And one of the example here is called the geometric mean. And there's a few more. And then we'll also break our data into things called quartiles, which represents 4 parts of the total data. There's a part from the 0 to the 25th percentile, which represents the lower 1/4 of the data, from the 25th to the 50th percentile, which represents from 1/4 to 1/2 of the data, then from 1/2 to 3/4, and then from 3/4 to the full population. Those are called quartiles. Quartiles are a collection of specific quantiles. A lot of terminology going here. Again, if we have a data model, we can create something called a quantile function, and it makes it easy for us, the human being, after it's programmed, to immediately determine where a numerical value lies in terms of the background database, in terms of its quantile, whether it represents a value that would be the biggest of all the data or the smallest or somewhere in between. The next terminology is variation. So we'll look at things called range, which is the upper bound and lower bound. Something called an interquartile range, which uses these quartiles and it identifies the breakpoints of them, and it looks at the 25th to 75th percentiles. Variance, which you probably had in your other classes, and the square root of variance, which is called the standard deviation, and the coefficient of variation, which, going from memory, I think that's the standard deviation divided by the mean. I might have that upside down. And then in terms of shape, we're going to look at something called the skewness coefficient. So let us begin. So centrality measures give us an estimate of the center of a data model. So I'm going to try to substitute the terminology data model for the word distribution, because our goal here is not to scare you yet. We'll do that on Thursday. The 3 measures of centering are the mean, the median, and the mode. The mean, also called the arithmetic mean, is the average of all the values in the data set. So this is an example of how we would write down the mean in a mathematical looking thing. X sub I represents each item in our collection, and we add all the items together. So this notation is the sum of x sub I as I ranges from 1 to n, where 1 is the index that identifies the first item, and n identifies the last item, and we include all the ones in between. So we add everything together, and then we divide by how many things there are, and we call that the arithmetic mean, or here it's called x bar, and this is standard notation. For those of you that know computational linear algebra, this is actually, the other way to do it is to do x transpose times the 1 vector, divide by the length of the 1 vector, and you get the same thing, but we won't go there. And don't even listen to that, I probably just confused the crap out of you. So let's look in our movies data frame at the column called budget in millions of dollars. If we extract the budget millions of dollars column and put it into an object named budget and then write the object, we have the following. So pointer 0 corresponds to 3.9, pointer 1, 237, all the way to pointer 9 is 306. So these are our budget millions of dollars. And let us suppose we wanted to ask the question, what's the average budget of the top 10 highest grossing films ever? And keep in mind, we're not correcting for inflation. That would be what I would do if I was working on Fox News or CNN in order to make the numbers look bigger to scare my viewers into buying some more crap at commercial time. So we can create a list of all the numbers in this way. So we'll have a new object called budget with a lowercase b, and this is just a manual entry. So someone entered a 3.9, 237, 200, and so forth. And we're going to calculate the mean, the object called the mean, which is the sum of budget divided by the length of budget. And that's a classical approach to arithmetic mean. And we find out that the average is $115.66 million, which for those of you without a calculator, if you had that much in your pocket right now, you'd be able to spend $1 million a year until the end of your life, and there'd be money left over. Which, you know, it sounds like that'd be kind of nice, actually. There's also a collection of external libraries that can do the same thing. And there's Numpy and Pandas, which are the ones you're familiar with. There's also SciPy.stats, which I've used before in demonstrations and just said type it and don't worry about it. And there's one called Statistics, and there's probably quite a few more. If we load these in, we can actually operate on them directly. So we assign move the column of budget millions to the object budget, and because we built that in the Pandas library, it actually has a method called mean already associated with it, and so we can apply the method to the budget object and return the same value. We also can use the Numpy mean function on an object, and as long as the object's a data frame or an array, it will be able to compute a mean value of it, and we get $115 million. The last example is, let's use the statistics package. So we imported statistics, and in that package there is a function called mean, which operates on lists, arrays, or data frames, and will compute the mean value of the list, array, or data frame. And we run that, and lo and behold, we get $115 million. So which one to use is, at this point, a matter of personal choice. Later on, as you're analyzing data, if you've done them in data frames or done them in arrays, you probably will want to use the methods that are specific to the package. And then if it's weird stuff, you'll probably be in SciPy or using statistics. And you may, as the programmer, have a little bit of work to do, because you might actually have to convert a data frame into a list, and there are methods to do that, and well, we'll use those as needed. A second kind of mean is a harmonic mean. So this is the preferred mean of street musicians, particularly those that play the harmonica, although the accordion musicians find it somewhat useful too. And in this case, the harmonic mean is the sum of 1 divided by x sub I multiplied by how many things there are. So the harmonic mean is a different type of mean, and it's useful in situations where the variables have particular behavior. It's still a legitimate mean. So let's look at the harmonic mean for the top grossing films. First, we will calculate it in primitive Python. So we take the length of the budget, and then we take the sum of 1 over the item for the items in the budget. This is a pretty cool structure right here, because that's the first time in a while that we've seen implicit looping over an iterable. The iterable is budget, and then there's a concept called an item, which is each member of the list budget, and so it's going to go through each of the items one at a time, divide the number 1 by that value, and then sum it up. And then we're going to report the harmonic mean by rounding to 2 decimal places. And do the same as in the statistics library. In this case, we just use the harmonic mean function in the statistics library. And then lastly, we'll use the SciPy library for harmonic mean to compute the same thing. And when we run it, we learn that the harmonic mean is $13 million. And then there's another one called the geometric mean, which is defined as the nth root of the product of all elements. And let's see what root we're going to use. And the n is how many things there are. And what we do is we multiply each thing by itself, running from 1 to n. So let's say there's 17 things. So A1 is the first thing, A2 is the second, A sub n is the 17th. And the key thing is geometric means we kind of hope that none of the things are ever 0, because that's going to kind of screw it up, because any 0 here will zero out the value. So let's look at the geometric mean for the same data. Again, in primitive Python, we will iterate for all the items in budget, and we're going to do multiply assign. So again, this is we haven't seen this in a while, and so gmean1 takes care of what's going on here within the radical. Then we're going to raise it, exponentiate it to the value of 1 over the length of budget. So we're going to raise it to the 1 over n power, or take the nth root of it, however you want to mentally think of that. Then we'll report it and round it to 2 decimal places. If we do the same using the statistics library, again we have the package name, and then the function name, and then the object we want it to operate on. We'll write it back out. And then lastly, we'll do it using the SciPy library .stats, and we'll use the geometric mean function, and we'll operate on budget. So we run it. Maybe it ran. Yep, it ran. And we see that there's roughly $35 million. And so here is a diagram that's might be useful to you when you're trying to decide how to be mean. If we think of things being on a circled map, and the things have kind of the same units or same magnitude, I mean roughly they're in the same power of 10, like numbers 1 to 300 versus we have 3 or 4 entries of 1s and 3 or 4 entries of 10,000s. So kind of close to each other in the same magnitude. We'd find the arithmetic mean is meaningful. Oh, good pun there. Alternatively, if they're vastly different scales, for example, if the data have some sort of logarithmic relationship to themselves, so we have numbers 1, 2, 3, 1,000, 2,000, 3,000, 10,000, 20,000, 30,000, 1,000,000, 2,000,000, 3,000,000, all in the same collection. The geometric mean is probably a better metric of central tendency. And then if the values represent rates, the harmonic mean is often preferred. If you want to know more about means, here's some useful references. First one is Arithmetic, Geometric, and Harmonic Means for Machine Learning by Jason Brownlee. And then I like the title of this one, On Average, You're Using the Wrong Average, by Daniel McNichol. And these are both blog links. So another thing I hope that we convey to you out of this class is this one blog called towardsdatascience.com. I think you'll find it pretty useful in other classes. So if there's a link to something like that, it's worth a visit. You may decide that that particular blog entry is not useful to you, but that's a good one to have bookmarked. I'm pretty sure I have it bookmarked on not on Firefox, but in my Safari browser. The next measure is the median. This one is actually pretty commonly used. It's fairly important. A lot of times it's a better measure of central tendency than any of the other averages because it has a statistical probabilistic interpretation. The median represents the 50th percentile of the data set. So that's half above, half below. So we're going to use the movies object, and we're going to pull out the gross, how much money the movies actually made, not what they cost, what they made. And we look at these, and these are ranging from 2.2 billion to 3.7 billion. Again, that's a pretty good payday. The arithmetic mean is probably going to be somewhere around 2.8 billion. But let's look at the half above, half below. We can just look at these. So 3706 is the biggest, so that's going to be above the middle. 3257 is big. 3081 and 3043. Those are the largest, and if we look at the smallest two, we have a 22, 22, 23. So the median is somewhere between 24 and 27, or 2.4 and 2.7 billion. So half the movies were above that and half below. And so again, we can create a list of the numbers, compute the length of the list, divide the length by 2, and notice that that's integer divide. And then for median 1, we will sort the list, and then we will round 0.5 times n minus 1, which is a formula for medians. And then we'll get the gross order, and finally assemble the half above, half below. And when we do that, we obtain a median value of 2.6 billion. So I wasn't bad in my visual guess. I just noticed I could have looked down there and saved a lot of time. We'll find that medians are quite a bit easier to do with external libraries. And all the external library is going to be is implementing some method, if not identical to, quite similar to this one, but it did a lot of the thinking for us, which is the whole point of using them. So we have the gross object. We will use the median method that's part of the Pandas library, and we'll have it print that out. Then we use the gross object, and we'll use the median function that's part of the Numpy library. And lastly, we'll take the gross object, and we use the statistics library median function. And we go to Fire, and we get 2.6 billion by the 3 methods. And then there's 2 more functions. One's called the median low and the median high, which works in instances where we have an even number of cases. So the main difference between mean and median is related to data sets, outliers, or extremes. The mean, the arithmetic mean, is strongly influenced by outliers. A cool example of that is, imagine if all of us were in a bar. Those are those places where people used to go to to have really greasy food and cocktails and then tell lies to each other until they were thrown out at 2 in the morning to make their way to the Whataburger on your way back to the dorm. Well, you guys might all be freshmen, so you didn't get to experience that yet. You will. Just wait. So we're all in there. And if we were to compute our average income of all of us, maybe there's 100 people in the bar, and we'd come up with some number. Maybe the average of 100 people in a bar is $50,000 a year. I'm making numbers up. Maybe it's more than that. And then Elon Musk walks into the bar. The average income of that bar just changed dramatically upward. It just went up to maybe $1.2 million a year. Does that mean the 100 people that were there all of a sudden got a pay raise? No. It means Elon Musk's income is so high that it has a dramatic effect on the arithmetic mean of income. Instead, if we calculated the median when Elon Musk walked into the bar, the median would only change a very little bit, maybe from 50,000 to 52,000 a year, whatever the break point is for the 101st person. And that's why the choice of central tendency is important. And in practice, you don't just do it willy-nilly. In this class, willy-nilly will probably be just fine. So the Elon Musk's value is considered an outlier in this statement. The mean is heavily affected by outliers. But the median is only barely affected. One of the uses of the two is to compare the mean and median as a way of detecting outliers and potential asymmetry in the data. And whether the value is more useful to you obviously depends on the context of the problem. The mean is the better choice when you can convince yourself that there's no extreme values exercising leverage on the metric. And it's a better summary because the information from every observation is included rather than the median, which is just the middle value. However, in the presence of outliers, median is a useful alternative. So here we have my bar example. So those are the elements in the bar that we had before, and so those would have a median somewhere around 2673 million US dollars. And then Elon Musk walks in, this guy, this 99999 guy. And let's see what happens when we do that. So we run that, and we had the original median of 2673, and then let me rephrase that. Elon Musk walks in. The mean value goes to 12,400, up from, get back up here. Someone needs to mute themselves. Thank you very much. Up from 115 million. Wait, I'm not supposed to be on the gross. Up from. Okay, I will do it. There we go. And then when the Elon Musk walks in, the mean goes way up because of his presence. If you want to read more, here's a few web links for you. Stuck in the middle with you, mean versus median, which one to use, and mean versus median by answer miner. And all of these, again, are blog resources and are worth visiting when you have a chance. The next measure is called the mode. And that's the value that occurs the most number of times in our data set. And it's tied to the concept of frequency, and it provides information on the most recurrent elements of a data set. If the mode is not unique, meaning that there are more than one mode, if there's two modes, it's called bimodal. If there's three modes, it would be trimodal. If there's more than three, we would use the terminology multimodal. Although here it's two or more. They're both correct. So let's find the mode in the top 10 highest grossing films. So we look at the gross, and here we have a 3700 and 32, 3081, 30. And the mode is we're going to try to find the count of the item that occurs the most frequently. And these ones, see if there's one that has 2. These are actually all unique values. We can use the mode function, the statistics mode function, and the SciPy stats mode function. And when we do that, we get the value that the mode in our first approach is just picking the biggest value. But in our case, our array has all unique values, so it really doesn't have a mode in the usual sense. A mode's not useful when the distribution is flat, but it does make sense when we are dealing with non-numeric value data, which is required in the case of mean and median. For instance, if we look at the string director in computer mode, we find out that James Cameron has more than one film in that list, and so he is the most frequently observed director in the top 10 list. He has 2. And then George Lucas and Steele. And if we went to beyond 10 movies, we'd have quite a few more modes. Excuse me, we'd have quite a few more candidates for a mode. All right, that should have you all pretty good and confused. So to learn more about modes, you can look at these blog entries, and they'll be useful. You will encounter modes later on in your education career in your probability and statistics class after this one. The key thing from a computational perspective, let's just look at the primitive list. This is something I would advocate you want to use a package to do, because if your list is long, computing a mode or the collection of potential modes can be challenging. Next is measures of dispersion, which describes how far apart data are observed. So let's return to our budget. We're going to look at the range. The lowest budget movie by my eyeball is 3.9 million, and the highest budget is 356 million. So the range is going to be 356 minus 3.9, let's call that 4, is going to be 352 million, that's all the range is. So it takes the biggest value and subtracts from it the smallest value and reports the distance between the two as the range. And that's useful, but it's not the whole story. And so if we run that primitive Python, we get the range of 352.1 million. And here the example is using a Numpy function called peak to peak that essentially provides the range. Now we're moving into good stuff, percentiles and quartiles. A measure which indicates the value below which a percentage of total data points in a data set fall is called a percentile. So imagine you have a bucket with 100 balls in it, and each ball is numbered. So there's a ball numbered 1, a ball numbered 2, and so on all the way to a ball numbered 100. If you were to take the balls out and put them in their numerical order, you would have the numbers 1 through 100. The first 25 balls would be called the first quartile of that collection, and it separates the collection into two parts. The part where the numbers are from 1 to 25 and the part where the numbers are from 26 to 100. So it represents the 25th percentile of that whole collection. The second percentile, the 50th percentile, which is also the median, breaks that collection into two pieces. Numbers 1 to 50 and numbers 50 to 100. And that second quartile also contains the first quartile, which is the break of 1 to 25, 26 to 50. And similarly, the third quartile is the 75th percentile, so it's going to divide between numbers 1 to 75 and 76 to 100. And it identifies roughly the largest quarter of the items in the data set. So in a simple mental model, that's really all a percentile and quartile is conveying, except that most real data are not buckets of numbered balls. And we can leverage these definitions and actually do so quite a bit. So let's look at the movies again, looking at the budget millions. So we're going to look at the create an object called P10, which is going to represent the 10th percentile. We'll create an object called P4070, which represents the 40th and the 70th percentile. We'll create an object called P10N, which is going to represent the 10th percentile. And then we will go ahead and describe the results of this. So let's look at what we're going to use. We're going to use the Numpy package. And in the Numpy package is a method called percentile, which operates on data frame objects. In our case, the object is the single column of movies, the budget in millions, and we're going to tell it to return the 10th percentile. So this second argument is the percentile you want it to return. If the second argument happens to be a list, it will return a list of the indicated percentiles, in this case the 40th and the 70th. And doing a similar activity with Pandas, there is a method in Pandas called Quantile, which operates on data frames. In this case, the data frame is a single column budget millions, and we tell it to return the 0.10 percentile or the 10th percentile, and it will tell us what value makes that so. And then the last one, the statistics quantile. Oh, that was a mistake. Let's see, Control Z. Statistics quantiles is going to produce a collection of quantiles. In this case, we've selected 4, so it's going to divide the range of 0 to 100% into 4 equal parts: 0 to 25, 25 to 50, 50 to 75, 75 to 100, and then return those values. So let's go ahead and run it. And it doesn't look like anything happened, but it did. So the 10th percentile of the top 10 grossest films is 7. The 10th percentile by Pandas is also 7, well 7.77. The 40th and 70th percentile is 11 and 211. That was by Numpy. And the 4 quantiles, so the breakpoint between the 0 and the 25th percentile, between 0 and 25th percentile is 10.6 million. From the 25th to the 50th is 10.6 million to 12. From the 50th to the 75th is 12 to 227.75. And from the 75th to the 100 is going to be whatever the max is. And we didn't tell it to report that. We can change that. Let's put the 99th percentile, so I can actually get that last quantile and run it. We'll see that the 99th percentile, which encompasses almost the entire database, is $351 million. And I'm hoping this will work. See if I get that 5th. Yeah, it's not quite dividing the way I expect it to. That's okay. From 227 million to 351 million, represents the 75th to 100 percentile. Related to those, and let me go back to, yeah, we're good there. Related to those is something called the interquartile range. So the interquartile range is defined as the value where the 25th percentile falls and the value where the 75th percentile falls, and the difference between those two. So we take the 75th percentile value, we subtract off the 25th percentile value, and by definition that's called the interquartile range. So again, using movie budgets, we'll take the percentile 75th, we'll subtract off percentile 25th, and we'll assign that to an object called interquartile range IQR1, and it will return those values. And we can use the SciPy stats package, which actually has an interquartile range function already built in. And if we run it, we'll see we get the same numbers. The interquartile range is often what you see in a box and whisker plot. The box part of it is the interquartile range. And actually that's coming up on the guitar shortly. So a last useful tool that we'll discuss is called the 5-number summary. And what it provides is it provides the median, the 25th percentile, the 50th percentile, the smallest value, and the largest value. And then those 5 numbers are very useful for any data distribution. And so let's go and remember our pandas and use the describe method on the budget object. And when we do it, we find out that the budget object has 10 things in it. The mean value is 115, the standard deviation is 140, the smallest value is 3.9, the biggest value is 356, the median is 12, the 25th percentile is 10.6, the 75th percentile is 227. So I want to call your attention to that number, that number, that number, that number, and that number. Those are the 5-number descriptions. And if we were to plot it in a box and whisker plot as done here, what we're going to find is the lowest number, the 25th percentile, the 50th percentile, I'm doing that wrong. 25th percentile, 50th, 75th, biggest number, lowest number would be a dot down here if there is one. And I believe this is also producing median and mode plots. And I don't use box and whisker plots analytically very often, but we will later on in this class. What we'll do is we'll compare series to each other, and if there was another one here, and the box was in about the same location, the purple line was about the same location, and the spread looked the same, and maybe there were 2 dots up here, we might conclude visually that that's the same kind of distribution, or if they're different, we would conclude that they're different. And we'll have some tests, some computations that support or refute those conjectures. Moving along in spread, there's variance, which is defined as the sum of the x sub I values minus their collective mean, quantity squared, divided by n minus 1. And so as written here, this is called a sample variance. If we're working and we have the entire population, then we don't have n minus 1, we have n objects. And the sample variance is a tool that represents how spread or how close the data are. Now bear in mind the sample variance is a squared value, so it's somewhat confusing because the magnitudes have changed. So you can't compare sample variances directly to means, but we'll show you a trick to do that. So the sample variance can be computed in primitive Python. First we compute the mean of the collection, and then we will repeat the computation in something that we'll call the variance, and we'll iterate through the items. We'll subtract off the mean we just computed. We'll square it, and then we divide by n minus 1, where n is the number of things, and that gives us the variance. And there is, in the statistics package, there's a variance function. We can apply that to the object. If we do that, we find out the variance is 20,374. But if you think of the units, that's going to be 20,374 millions of dollars squared. So I don't know what a square dollar is. Maybe it's like a square deal. So what we use often instead is the standard deviation. And in the standard deviation, we can take the square root of the variance, and that would be the standard deviation. And the reason the standard deviation is attractive is it's in the same units as the data points. And so again, repeating the primitive and the statistics calculations, we find out that the standard deviation for the films is $142 million. And so at this point, the reason we can report that the average budget is $150 million plus or minus $142 million. That represents one standard deviation. So Ileana, the reason that we square the variance is actually the variance is something called a second moment of the underlying data model. So it's theoretical, and it's actually what gets computed. And then the standard deviation is the square root so that we can discuss stuff in terms of the same scale as the mean values. So the point of the absolute value bars, I misunderstood your question, Ileana. The point of the absolute value bars is those variables x don't necessarily have to be real numbers. They can be complex numbers, and so they can have an imaginary component to them. And the electrical engineers will learn a whole lot about that. And so by absolute value, you're guaranteeing that you get the real part out of the summation. And then the last metric we're going to look at, we didn't look at a coefficient of variation, but we can, I think I can pull that up real quickly on a quick Google search. I think it's relative standard deviation. My other good friend is Wikipedia. Trying to go from memory. Coefficient of variation is standard deviation divided by the x bar. So if we wanted to introduce coefficient of variation here, we would just have COV is it's the mean. No, it's see. Oh, I'll just do it the lazy way. And let's before we actually run it, let's try to get a mental image of what it should be. So the standard deviation's of 142, and the mean value. Are we on grosses? We're on budgets. So the mean value was 511 or something, 352. So we're going to have a 142 divided by 352. So our coefficient of variance would be about 0.3. And sure enough, it won't work. Let's try that again. Ooh, it's just refusing to run. Huh, that's funny. Oh, it's also, it ran just fine. Let's actually look at the value. I'm mentally misinterpreting that, but 142 divided by 300. Okay, I'll take take it on faith for that. That was just a quick Google search and didn't read it close enough. But coefficient of variation is actually fairly useful in comparing items. The next metric that we want to examine is called skewness. And this measures asymmetry of a data sample. There's quite a few definitions of skewness, and this one here is called the Fisher-Pearson one, and we're going to use it today and actually the next few times for measuring skewness. And let me see if I can come up with a picture of a skew distribution for you.
If you scroll down, I think I have put a picture in there. No?
No.
Okay. I'm going to send it now.
Oh, I'll actually get one from... See, I think I have one on a presentation. This one should be good enough. I might probably have a little idea of what skew is. Oh, it's gone to spinning beach ball. I'm trying to get the picture of skew. Nope. Oh, come on, machine. Picked the wrong one. Let's see. 2018, I think it's, yeah, this one should have a good picture of skew. Okay, so, oh, that's not the picture I was after. Imagine a data model. So don't worry about the word probability distribution. It's a data model. If the data model is symmetric about some measure of central tendency, as shown in this black line right here, the left side and the right side kind of look like each other. They look like mirror images of another. If the data model is skewed, they're no longer mirror images. One side is longer looking than the other side. In this case, longer looking than the other side. And this dashed line here is representing a symmetric distribution. So skew has importance in risk management because if we think a data model is symmetric and it's not, we will make poor decisions from a risk perspective. So that was the picture of skew. Oh, I could have left that up for kurtosis too. So skewness measures how shifted from symmetry a distribution is. And the actual calculation, we compute a value n-1, we compute another value n-2, and we'll again perform a summation. In this case, we take the observation and we subtract off its mean value. We divide that result by the standard deviation of the entire observation set, and we cube it. We sum that up, and then we weight it with n over n-1 times n-2, and that is called the skew coefficient. If the skew coefficient is close to 0, we consider the data set symmetric, and that has some useful implications. If it's not symmetric, we have to perform some different modeling manipulations to make use of it. In this case, all we want to do is compute this descriptive statistic. And so let's go ahead and run it. The first one in primitive actually just implements that formula that's right above. The other one uses the skew function in SciPy, and then the other one uses the skew method that's part of Pandas. I didn't know Pandas had skew built in. That's really cool. So we run it, and we find out that skewness of films is 0.76, which is positive, less than 1. I should have left my picture up. In fact, let me see if I can go and leave my picture up and make some interpretation. So we have positive skew, which we're slightly long-tailed to the right, and So what we have with our movie distribution, the magenta line here is symmetric, and because we have positive skew, some of our lower value numbers are shifted to the right. In movies, I don't know what that means. In natural resources, that has implications for frequently recurring values. But it's kind of close to the doesn't really matter range. It's a little bit bigger than a half, and so you would probably apply adjustments to the data model. The other metric is called kurtosis or pointiness, and what it does is it measures the length of those tails that were shown in the pictures. So how far out to positive and negative infinity does the data model actually run? Theoretically defined between minus infinity and plus infinity, but if we were to use, for example, the classroom grades in a typical teaching class, maybe there's 100 people in it, the lowest possible grade is a 0. The highest possible grade is 110, because you can always get 110% if you submit the appropriate bribe check at the appropriate time. I'm kidding on that. Highest is 100. So that distribution doesn't have any meaningful tails less than 0 or bigger than 100. That data model. So we're going to look at the kurtosis of the budget. I think with this we'll have the same features, is we don't have any meaningful negative tail, and we'll just calculate the kurtosis coefficient. So the kurtosis is literally just the fourth moment. So it's the observation minus the average value of the collection raised to the fourth power divided by the standard deviation raised to the... Is that standard deviation or variance? I always... Divided by variance raised to the fourth power weighted by 1 over n. And the value of the kurtosis coefficient in terms of its magnitude relative to 1 is used to determine the amount of pointiness. And so if we run it, we're just going to use the kurtosis calculation that's part of the SkyPy package. We can learn more on skewness and kurtosis going to the NIST. So that's National Institute of Standards and Technology. This one is actually going to provide some detail on the actual calculations. Here's another one that questions whether they're useful or not, and I would argue they probably are. Skewness is certainly useful. Kurtosis, I'm not sure how to use that in any research I've ever done. And then two terms you must know, and then Skewness and Kurtosis by Stan Brown. I'm going to go to Mr. Diva Dugar's thing, and let's see if he has good pictures. I'm pretty sure he does. So his pictures are way better than mine. Cool. And then kurtosis. So kurtosis is often introduced the way I just did, the measure of the peakiness, but it's actually a measure of how far out the distribution ranges. And if the kurtosis is bigger than 3, it's this flat distribution, and there's a lot out there in the extreme range. And if it's smaller than 3, the tails are thinner, and it's more of this pointy case, and there are limited range. In our case, it was smaller than 3. It was 1.7. Actually, it was negative. So we have a very bounded distribution, or data model, if you will. Okay, I think I've confused you all pretty thoroughly, and sounds like domain. Yeah, somewhat. So what we've introduced today is descriptive statistics, and I've introduced them as simply computations we make on things. We got a teensy bit of theory, not just enough to be dangerous, which is ideal, but not enough to make any sense of it. I'm curious how this thing returned a negative value when we're raising stuff to the 4th power, because that's the square of a square. I won't worry about it. For these descriptive statistics, the lab is we just want you to implement them. And then next lesson and a few other lessons, we actually use the descriptive statistics to fit our data models to our observations. And again, that will be explained mostly as just a procedure, and you will pick up the theory in other classes. You can get the theory of this in other classes. So all we're trying to do now is kind of put these ideas in your head so that a year from now, when you're in your probability and statistics class, the words don't sound so foreign. You'll be able to say, "Oh, I saw that before in that crazy computing class that those two guys taught us," and you'll know how to do it. So that should be hopefully a competitive advantage for you over other people in the class. And with that, I am going to. Oh, I want to show one last thing, and then I am going to turn this over to lab. Okay, so we've run this notebook, and I ran it on my local computer. Let's suppose I was going to hand this in. Actually, I want to run the whole thing completely. Run all. Okay, so I wanted to run a copy, and now let's say I want to hand it in. Remember in CoCalc, we would have export notebook as, well, we don't have an export option. We're on our own home computer, and my own home computer is actually talking to itself, but it thinks it's talking to a website. And so it gives us the option to download as HTML, PDF. I'm going to choose PDF. No, I don't want to choose PDF. If you choose PDF and you get a error message that says NB convert failed, perhaps you don't have XE LaTeX installed, that normally would be a deal killer. But let me show you something cool that I discovered yesterday. I'm going to export it as an HTML. And I will just save the file. And let me show you that I saved the file. Sure enough, HTML got all the graphics and everything. Woohoo! But we know we can't upload that to Blackboard. Let's make sure it's still there. There it is. But we can do something cool, which is we'll go to a website called html to pdf.com, and when we get this website. So let me give you all a warning. These green buttons, those are requests for money. Stay away from them. Don't even go through this unless you know exactly what you're getting into. I think the extension is free, but I just don't like that idea. But we're going to go to Upload Files, and I'm going to go ahead and I hope I can find it. What was it called? Lesson 12 HTML. And yeah, I just did that. So I'll go ahead and do that, and it's now uploading to their website. And when it gets there, it's going to start the conversion process. Okay, so now it claims it has converted the file into a PDF, so let me go ahead and download it. I will choose the okie dokie. Let it get here. And now I have a PDF file, and I can upload that to Blackboard. So while that's admittedly one extra step that you wouldn't have to do if you had a correct XE LaTeX installed, it saves you from having to go to the trouble of installing XE LaTeX. And it does a pretty good PDF rendering of the file. And this stuff where it clips is pretty typical when you go HTML to PDF. I don't think it's going to have much of an impact on any of your guys' work, because Farang and I are smart enough to be able to read through this and figure out what was going on. So now you have seen all the tools for doing this on your home machine. Today I did Macintosh. On Thursday I'll do the same thing, but I'll use Windows. So remember, it's html to pdf.com. And then avoid the big green continue things. I guess they make their money by suckering you into clicking on the green things, because you end up having to watch commercials. I don't need to send that to him privately. I want to send that to everybody. There you go. So now you have new tools in your toolkit. Let me exit that, and I will stop sharing, and I will hand over control